So now we're going to get into the mathematical background that we need for this class, mathematical preliminaries. And we're going to talk about what we need to know about differential equations. So ordinary differential equations. And we're only going to need one technique. When you take differential equations, you learn 143 techniques or something. We need one of them. And this is the one that, in my experience, for the whole rest of your time in mechanics, in electrical engineering, you tend the sort of go-to techniques are different techniques. But in all the mechanics classes, if you're ever in a class expected to solve a differential equation without them first giving you a refresher on a certain technique, this is the way you solve it. This is the only one people are going to hold you accountable in the future for. The easiest one. I think to me, the most difficult thing about differential equations that you might see in the future is just making sense out of what are you trying to solve for, what's the independent variable, what's the dependent variable. So we'll talk about that stuff a little bit. But solving, once you have figured out what the question is, solving it is really easy. And then a couple of things that you probably just haven't seen very often in this format. So we're going to talk about derivatives of vectors. And these are going to be in non-rotating coordinate systems. Up to this point, most likely all you've ever seen are non-rotating coordinate systems, but there are a lot of cases in dynamics where you need to deal with rotating coordinate systems. It sounds like a disaster. It's pretty interesting the way the math works out. I think it's a cool part of this class. But like, for example, I'll go into, I'm not going to go into much detail now, but if you're dealing with any kind of aerospace application, you can think of your coordinate system as defined by the camera that's taking the measurements. You can always think of a coordinate system as sort of equivalent to a video camera. And you don't have the luxury of having your camera fixed in space, observing what's happening. Everything you're trying to observe is flying through space, and that airplane or that satellite or whatever is the only place you can fix a coordinate system, and that thing's rotating. So your measurements just have to be taken in a coordinate system that's rotating. That means it's not inertial. That means Newton's second law and the moment equation don't apply in that coordinate system. And so you have to do some figuring to come up with new versions of those equations of motion. And so a big chunk of this class later on is going to be re-expressing the equations of motion in rotating coordinate systems. We're going to start with, in these mathematical preliminaries, we're going to deal with derivatives in non-rotating coordinate systems, the easy case, but what we're going to do here doesn't hold if the coordinate system is rotating. And then product rule with vectors. And the chain rule with vectors. Okay, so this is going to be it's not really going to be that long, but we'll spend the most time on this, and then all of these are going to be really short. And once we're done with these, we'll be able to go on to some dynamics finally. Okay. So first, ordinary differential equations using separation of variables. Um, so email me later if I'm wrong about this, but I think it's going to be the case that this is the only one you're ever going to be held accountable for without a reminder. So listen close. So if you're given, first let's talk about ordinary uh, versus partial differential equations. Um, so an ordinary differential equation, people always abbreviate that ODE, is one where there is a single independent variable and you're trying to find one or more dependent variables that are functions of the independent variable. Okay, so let me give a couple of examples. So y double prime plus 10 y prime plus y prime y squared is equal to 50y. Okay, that's it doesn't look that terribly complicated, but that would be a brutally hard differential equation to solve. And actually, let me change this to 50x. Okay. So what are we trying to find here? So in this case, x is the independent variable. There's only one of them. And we want to find y of x. How do we know that there's only one independent variable? Well, the fact that I'm using that prime notation is sort of an indirectly tells us that that's the case. Because if there was another hidden independent variable in here, like say this function y depended on x and c, we wouldn't use this prime notation. We'd use partial derivatives. Okay. We'd say this was the second partial derivative of y with respect to x. Here's a second one. Let's say dz dx times the square root of x is equal to 50x. Again, there's no partial derivative. We're told explicitly that z is a function of x. That's what that notation means. And so what are we trying to do when we solve this equation? We know that x is the independent variable. And we want to find z of x. Another example we could see is, so let's say dx dt is equal to 10t, and dy dt times t squared is equal to 5. Is that an ordinary differential equation or a partial differential equation? This is an ordinary differential equation. The difference is we still only have one independent variable, that's t, and x and y are both functions of t. Okay, so we can be solving for a million functions and still have it be an ordinary differential equation. T is the independent variable, and we want to find x of t and y of t. Okay, so you can have any number of functions you're solving for as long as there's only one underlying independent variable. So let me give an example now of a partial differential equation. The partial of z with respect to t plus the partial of z with respect to x plus the partial of z with respect to y is equal to 1. And that's a partial differential equation because we have 3 independent variables, t, x, and y, and 1 dependent variable. We're looking for z, which is a function of t, x, and y. Okay. So the difference between those two things is, are we looking for functions? Are we looking for functions or a function of one variable? Or are we looking for functions or a function of multiple variables? And you can tell what you have based on what you're taking derivatives with respect to. If you're taking derivatives with respect to a single thing, it's an ordinary differential equation. If you're taking derivatives with respect to multiple things, it's partial. And it's given away by the fact that in PDEs, the derivatives are always partial derivatives because you have multiple independent variables you can take derivatives of. Anybody have any questions about that? So the key is, are they functions of one variable or functions of multiple variables? Okay, so separation of variables. And even this gets a little confusing because there's a partial differential equation technique called separation of variables that's unrelated to this. It's just, those are the names that are chosen. So separation of variables is when you have something like this. And I'm going to say, well, I'll write it like this. dy ds is equal to a function of y times a function of s. Can't ask anything. In this class, our underlying independent variable. So in this case, s is a single independent variable. And we want to find the function y of s. Usually our independent variable is going to be time in this class. So t will be our independent variable, but this is just sort of a general way of writing this. So since there's only one independent variable, this is an ordinary differential equation. And the way you solve this is get all the, so what's notable about this differential equation? What is it about this? So you can't solve every ordinary differential equation with separation of variables. So what's special about the things you can solve by separation of variables? What's special is you can break it up into two things multiplied together. A function only of the dependent variable times a function only of the independent variable. Okay. Like, let's look up here above at some of these examples and see if any of these are of that type. Okay, so in this one, the dependent variable is x. The independent variable is x. The dependent variable is y. Can we express this as a derivative? Well, we can't do it, but this is a second order derivative. Let's forget about that for now. We could deal with that step by step, but let's go to these two. Okay, are either of these two of a form where we could express this as the derivative of the dependent with respect to the independent is equal to a function of the dependent times a function of the independent? That's what we're looking for. So let's look at this one. So dz dx, and we can get that by itself by dividing both sides by that square root. And if we do that, we have dz dx is equal to 50 times the square root of x. Okay. 50 times the square root of x, is that in the form of a function of the independent times a function of the dependent? It is, because you can think of 1 as a function of the dependent variable, and so this one we could solve with separation of variables. Okay. What about this one? Well, it's sort of the same form. We have a function t multiplied by 1, which is a function of x, and so we can solve that one by separation of variables. This one, though, there's no way to, let me give another. example. Let's see. You don't have to write this down, but let me just write down one that you can't solve by separation of variables. So let's say we have dx dt plus x plus xt is equal to 1. That you could too. So let's do, okay. So what if we have that? So dx dt times t plus x plus xt is equal to 1. So dx dt times t is equal to 1 minus xt minus x. Then divide both sides by t. And you get 1 over t minus x minus t. Okay, so is there any way to express this as a function of t times a function of x? No. And so this is an example of a simple looking differential equation. There are ways to solve this differential equation that aren't hard, but you can't use separation of variables. But so if you have something that you can separate that way, okay, you can separate into a function of the dependent variable times a function of the independent variable. And the way you solve that is rewrite this. This is a little bit of a, I don't think this is probably the way that like your math teachers would like you to think about this, but I think this is the way I always do it, and I think it's a nice way to think about it. So we'll get everything that is a function of the dependent variable on one side, everything that's a function of the independent variable on the other side, okay? Which means we'll go dy over f of y is equal to g of s ds, okay? And now that we have this infinitesimal y here, this infinitesimal s here, we can just integrate both sides. And when you take that integral, you can solve for that function. This gives us y as a function of s. Okay, let's do a couple concrete examples. So first, let's say y dot is equal to y squared times t squared, where y of 0 is equal to 10. Has anyone seen that dot notation before? You know what that means? So anytime you see a dot, that's just saying that's a first derivative of that variable with respect to time. So dot always means time. We're going to use that all the time in this class because the main independent variable we're going to use is time. We're going to have functions of time everywhere. Okay, so I'm going to rewrite this as dy dt is equal to y squared t squared. And so y to the negative second dy is equal to t squared dt. And I'm going to integrate both of these. So we get y to the negative 1 over negative 1 is equal to t cubed over 3. And each of these has a constant of integration. I can just combine those into a single constant because they're both arbitrary. So I'll just call this plus c. Okay, so how are we going to find that constant c? Well, yeah, we're given that boundary condition that says when time is equal to 0, y is equal to 10. And so I can just use this equation here, put in 0 for time, put in 10 for y, use that to solve for that constant c. And then at that point, all I'm trying to do is isolate the variable y and express that as a function of time. So the boundary condition says negative 10 to the negative 1 is equal to 0 to the third over 3 plus c. So c is equal to negative 1/10 or negative 0.1. And now I'll use this to update what I know about the function. So I know that negative y to the negative 1 is equal to t cubed over 3 minus 0.1. So y to the negative 1 is equal to negative t cubed over 3 plus 0.1. And this is 1 over 10, 3 over 30. So I think this is equal to negative 10 t cubed plus 3 over 30. And now I can just take the reciprocals and I finally get that y is a function of time, the thing we're looking for. You can do second order ones this way too. So the second order means that the highest order derivative in the equation is 2. That means that first example we did was a first order ordinary differential equation. And so let's do one that says x double dot is equal to 2t squared, where at time equals 0, x is equal to 2. And at time equals 2, the first derivative of x with respect to time is equal to 4. Okay, so I'm going to do this step by step. First, I'm going to think of this, the second derivative of this with respect to time. You can think of that as d dt of x dot. And so I'm going to write it that way. Just deal with one of those derivatives at a time. So d dt of x dot is that x double dot. And that's equal to 2t squared. Now my variables for this step are, so the independent variable is t. The dependent variable is x dot. We have this written in the form that we need for separation of variables. This is a function of time times 1, which we can think of as a function of x dot. So we can use separation of variables. Separation of variables is just integration. So you can also just think of that as the fundamental theorem of calculus. And so we get dx dot is equal to 2t squared dt. And now we can integrate both of these. What do you get when you integrate dx dot? X dot, yep. Just like when you integrate dy, you get y. When you integrate dx dot, you get x dot. So x dot is equal to 2t cubed over 3. And I'll combine the two constants of integration. And in this example, now we can use one of these boundary conditions. So we'll use the boundary condition for x dot. It says that when time is equal to 2, x dot is equal to 4. So plug those conditions into this equation. So we have, so there's the 2 for time plus c is equal to x dot 4. And we can use that to solve for c. And so that's what, 8/16 thirds, 4, 1 1/3. So You get negative 4/3 there. Yeah. Okay, so now I'm going to update. Before we use that boundary condition, so x dot as a function of time, at off, but it is a function of time, is equal to 2t cubed over 3 minus 4/3. Any questions about that yet? And now the second step, x dot is dx dt. So we have dx dt is equal to 2t cubed over 3 minus 4/3. So we get multiply dt to both sides, and we get dx is equal to 2t cubed over 3 minus 4/3 dt. Integrate both sides. What do you get when you integrate dx? X. And over here you get t to the 4th over 6, I think. And then minus 4t over 3 plus a constant of integration that you get from the combined sides. I'm going to call that C2 this time. How are we going to get that C2? Yeah, the second boundary condition. And now you see why in this case, like in that first example, wherever it was, we only needed one boundary condition. In the second example, we need two boundary conditions. What do you think the difference is? The order. Yep, you need the number of boundary conditions equal to the order of the differential equation. And so the boundary condition says when time is equal to 0, x is equal to 2. So the boundary condition says 2 is equal to 0 to the 4th over 6 minus 4 times 0 over 3 plus C2. So C2 is equal to 2. Now we know a little more, so I'll update that again. And our final answer is x as a function of time is equal to t to the 4th over 6 minus 4t over 3 plus 2. There's one thing I want you to notice from that one. For an ordinary differential equation of order n, you need n boundary conditions to solve for the constants of integration.